Hello, in this video we're going to look at how to combine vectors using components. If you recall today in class we looked at how to combine vectors graphically using this example. We started with this example where we have a box being suspended by two different ropes and gravity is acting down on it and the two ropes are acting in these other directions. And we showed that if you create a graphical picture here, drawing the vectors to scale and using the correct angles, you'll see using the head to tail method that the vectors all come back around to create a closed figure, which indicates that the vectors all add up to 0. We'd like to see in this video how to do that analytically without having to draw the diagram. And we need to do that. We need to start with a little basic trigonometry. So I assume that most people watching this video probably know some trigonometry already, but if not, you can find lots of good resources on the web to help teach you how it works. But the idea is if we've got a triangle, right triangle, and the sides of the triangle are related using trigonometric functions. So the sine of this angle theta is equal to opposite over hypotenuse. The cosine of the angle is equal to adjacent over hypotenuse, and the tangent of the angle is equal to opposite over adjacent. And usually what we'll be doing for this operation is using either the sine or the cosine to solve for the length of this opposite side or the adjacent side. So let's look at how this works in practice. So we're going to start with the same diagram from the first problem, and we have these three different vectors. So I'm going to start with vector A here and redraw it over here. And the idea with resolving these into components is we want to take this vector that's at an angle and figure out its horizontal and its vertical components. How much of this 90 newtons is acting in the x direction, and how much is acting directly in the y direction. And so we'll use our trigonometry here to do that. So the figure we were given, this 49-degree angle, is where the 90-degree is relative to the vertical, and I changed this into 41 to figure out that angle relative to the horizontal. It doesn't matter which angle you use, it's just that usually we have a reference angle relative to the horizontal. So to figure out how much of this 90 acts in the horizontal direction, we take 90 times cosine of 41, which equals 68. And to figure out the vertical component, or the y component of this vector, we take 90 times sine of 41, which gives us 59 newtons. You want to be sure that your calculator is in degree mode when you're using these trig functions for this kind of operation. And usually once you get your numbers, you can kind of take a look at them and usually have some idea of whether you're on the right track in terms of the size of these numbers compared to the hypotenuse. So it makes sense if this were 45, then these would both be equal because you would have a 45, 45, 90 triangle, but we're a little off, but the numbers make sense. So then we'll go on to the next vector, which is vector B, which is pointing kind of in the opposite direction. So we're given the hypotenuse is 79, the angle relative to the horizontal is 31, and our horizontal component is 79 cosine of 31, which is 68, and our vertical component is 79 sine of 31, which gives us 41 newtons. So now we've resolved both of those vectors, A and B, that are at an angle into their horizontal and vertical components. And now we can combine everything using a little force table. So we line up our forces here and we write down their x and their y components. And this is the point where you have to pay attention to the direction. So we're assuming a coordinate system that's centered at the origin at this little black dot. So anything to the right is positive in the x direction and up is positive in the y direction. So consequently, A's components for both the x and the y are both positive. And B's components are, the x component is negative because that negative, the force is to the left, and so the x component is negative 68. But the y component is pointing up, so it's positive. And then the force C, we didn't have to do any trigonometry on because it's all just straight in that vertical direction. So it has 0 component in the horizontal direction, and all of it is acting downward for negative 100. So we can see once we put these forces into their x and y components, we can just add them together because they'll all collinear. When the A and B forces, the 79 and the 90, we can't add together when they're at those angles. So the whole point of using trig to put these into components is to make it easier so that we can add these up. So we see that the sum is 0, which is what we expected, that all of these forces balance each other. So for the next step, I'd like you to try a practice problem. A 10-kilogram block moves horizontally on a surface when a force of 45 newtons is exerted on it at an angle of 25 degrees as shown. The frictional force is 30 newtons, the normal force is 79, and I'd like you to find the net force on the block in both the horizontal and the vertical directions. So I'd like you to pause the video at this point, get out a piece of paper and your calculator, and see if you can find the answer to this, and then you can come back and unpause it, and I'll show you the solution. So here's the solution to the practice problem. I've drawn my free body diagram to show the total of 4 different forces acting on the object. We're given that the normal force is 79, the frictional force is 30, the weight we can calculate because we know the mass, and we're given the applied force. So we can summarize these in our table, paying attention to the directions, as you can see, and the only one we have to use any trigonometry on to resolve into components is the applied force. So we've got the 45 cosine 25, which gives me the x component, and the 45 sine of 25 gives me the y component. When we add those together, we get this result. So the net force is 11 newtons in the horizontal direction, and that makes sense that there is 0 net force in the y direction because the object maintains, it doesn't rise off the ground, so it doesn't have any motion in the y direction, so the net force in that direction will be 0. So the next step would be to go back to this homework assignment we had today and do the rest of the problems, and rather than adding them graphically, see if you can add them analytically and get the same answers.